Hello and welcome to the second lecture. This is Viscosity and Shear, a lecture that I love to give in person because we get our hands dirty. I'm going to post for you guys, I'll talk about this a little bit later, but I'll post a video that something that y'all should play with at home is basically to make some oobleck. Some of you guys, depending on, may have done this in middle school or even grammar school, and it's super cool and we're going to talk about it. It's like a 5-minute video from some lady. And it looks like, the video is made for kids, but I'm going to recommend it anyway. It's kind of something fun you can do. Anyway, so today we're going to be doing viscosity and shear, and the objectives today are we're going to define absolute or dynamic viscosity and kinematic viscosity. So these are two different viscosities. They're related mathematically, and we'll talk about them. So there's the absolute viscosity, and then there's the kinematic. And then we're going to apply Newton's law of viscosity. Like everything, Newton figured it out. And then we're going to talk about how you can talk about different fluids based on their viscosity. In this course, we're really only going to deal with one type of fluid, that's a Newtonian fluid. But for today, we'll mention some of the other types, just as something you should be aware of if you decide to go into a fluids-related thing, or if, for example, you are suppose you're a mechanical engineer and you have to deal with some of these other fluids, or you're a naval engineer or a civil, I guess, and you're working on a model or something, and in your model you're like, I'm not going to use water, I'm going to swap out for honey or some other fluid, and maybe it's not Newtonian. It's a good thing to be aware of. Okay, so we'll kind of talk about that as we get to it. Okay, so first of all, what is viscosity? Okay, so viscosity is a measure of a fluid's resistance to flow. That's kind of the kind of a typical way to describe it. It describes the internal friction in a fluid. So I guess, you could think of this as like friction. Okay, I mean, this is almost kind of like the key word, but there's reasons for it. And so one of the things that kind of like one of the ways that I think about it is, suppose you had like a cutting board or something in your house, okay, and you put a big glob of honey on it or something. Okay, and so the glob of honey may start like that, and then eventually it's going to kind of start to flow a little bit, and eventually it's going to start to kind of do like this, and eventually it's basically flowing down the thing, but it's taking a long time. Okay, and of course we're engineers, we're scientists, we're mathematicians, and we want to describe why that happens. I mean, the same thing would happen with water, but it would be a lot quicker. But the question is, why? So mathematically we say, well, we're going to define this as something called a viscosity, which has this symbol right here. So that's a mu, which I guess would be written like this if you were like on regular things. So it's a mu, and that is the viscosity. Okay, so I guess I could have put it right here, the mu. It's like a U with a long tail. Anyway, so we're going to describe it mathematically, but it's important for us to understand molecularly what's going on. Okay, and this internal friction is all due to molecules. So basically, as this thing is trying to flow down, as this honey is trying to flow down this, cutting board, okay, we can imagine that basically the external forces on this honey basically is there's some friction along the bottom. Okay, if this were a free body diagram of the honey, okay, there's some friction along the bottom, and there's some gravity kind of going downwards, okay? And if we were to combine those two forces, or if we were to, turn our, if we turned our coordinate plane like this, okay, so that we were kind of, in the direction of the board, we could see that basically gravity's pulling it to the right, and the friction is pushing it to the left. Oh, I guess there's a normal force in here too, if we wanted to be absolutely full, complete. So we got a normal force, we've got gravity, and we've got a friction, okay? And that's all external, okay? But what the fluid feels, like if we just kind of look at just the fluid itself, so if I'm, a glob of honey, so I'm going to go ahead and rotate this so that I'm thinking about the honey, as if this is X, and this is the X direction, this is the Z direction, or the Z direction. Okay, so I'm just drawing and I'm just turning it a little bit, just because it's kind of going to be easier for me to draw or think about. Okay, so now I've got this honey, okay, and I'm only thinking about the honey. Okay, well, that honey's got a force along its bottom, which is this frictional force, right? And it's got gravity, which is kind of acting all along this top bit, right? Okay, so, it's acting to the right, okay? And that's this component right here, okay? The gravity and the x direction. I'm only doing x forces right now, okay? I don't care about the y forces. Okay, so what's happening here, if we think right in this region over here, is there's a lot of shear. Okay, basically because of the friction is to the left and the forces above it are to the right and they're not aligned, the tendency of the fluid is to want to fold over, right? Basically this wants to keep going this way, while this bottom bit kind of wants to stay where it is. Okay, so ultimately, the fluid kind of wants to shear in this direction. Okay? So this is the shear stress that is being applied to the honey to move to the right, okay? And it's because the friction at the bottom is kind of holding it in place, okay, it's going to flow fastest along the top, okay, because that's farthest away from that friction. Okay? And yet still, though, it should be apparent that this one right here, okay, this layer of fluid right here, of honey, okay, let's zoom in a little bit. This layer of fluid on the top, okay, is not acting completely freely, right? It's being slowed down by this layer underneath it, which is being slowed down by the layer underneath it, which is being slowed down by the layer underneath it, which is being slowed down by the layer underneath it, which isn't even moving because it's got this friction from the bed, from the cutting board. Okay, so the question is, how do these fluid layers affect each other? Okay, so the way that they affect each other is, and I'm going to draw them as if these layers were completely discrete. Obviously, they're continuous. Okay, so let's imagine we've got a bunch of layers, and they're all moving at different speeds. Okay, so they've moved, different lengths and different speeds. Okay, so here's like a whole bunch of layers. All right, so one of the things that's going on here is that you have a molecule right here and you have a molecule right here. Okay, and they like each other. Okay, this goes back to that cohesive forces, okay, so, or cohesion, okay? And because they like each other, they're gonna pull on each other. So this one right here is being pulled backwards by that one, and this one is being pulled forward by that one. Let's zoom in if we can. Okay, so what's happening is this one, which is generally fast, is being pulled back. And this one, which is slower, is being pulled forward. Right? Okay, similarly, okay, in this one, okay, is being pulled forward by its attraction to that one. Right? And this one is being pulled backwards by its attraction to this one. Okay, so this same relationship exists amongst all of these layers, and the net effect is that if you give it time, okay, if time happens and there's no more, and all external forces are removed, then eventually they'll all be moving at the same speed. Okay, all the layers will be moving together. Okay, eventually. Okay, so basically, this profile of like faster on the surface and slower down near the bed will basically turn into something more like this if you give it enough time. Okay, and that's because the molecules are going to be pulling on each other and they're going to be basically exchanging. If you're going too fast, you're going to be pulled to slow down by the other ones around you, and if you're not moving, you're going to be pulled by the ones that are moving, and so you're going to tend to gain momentum. Okay. So that's one reason for viscosity. Okay, so I need to go up here and up here, and we want to say basically this happens for two reasons. One is cohesive forces. Cohesive forces, okay, between the molecules. Okay, the other reason is I'm going to call it molecular exchange. Okay, and this will be the exchange is going to be really, really important as we get into the semester. But let's go down here and I'll talk about it real quick. I'm going to end up talking about this one an awful lot, especially when it comes to turbulence. It's more important than it is in these kind of molecular viscosity. But again, let's consider a bunch of layers of fluid. Each one is moving at a different speed. Okay, so this one's moving really, really fast. This one's moving less fast, less fast, less fast. And the bottom layer is not moving at all. Okay, so if we've got this situation, another way that essentially the fluid is always trying to equalize, like it's always trying to get where everything's moving the same velocity. And another way that this does this is through molecular exchange. So the molecules are all in here, and they're all jiggling around and doing their molecule best to be, happy little molecules. But what happens when one that's up here, okay, because it's jiggling, it jiggles down here. Okay, it's got high momentum because it's in a high momentum layer, okay, or high X momentum. As it jumps down, okay, into this lower level, okay, it is going to tend to increase the momentum in this layer, okay, and that will then increase the velocity of that layer, okay. By the same token, okay, if we have a molecule here and it jumps up there, okay, this is a lower momentum, okay, and so when it goes up into the upper layer, it is going to decrease the momentum up here, okay, because it is basically moving slower to the right than the ones around it, and so it's going to decrease the X velocity. Okay, and the same thing will happen on any layer. So if we have these two layers and we have two molecules and they exchange, okay, it's going to cause them to get closer to each other. The momentums, the velocities are going to try to equalize, okay? And that is because of the exchange between the two molecules. Okay, now note, okay, so that's how molecular exchange, and the effect of both of these is the same, okay? It works in the same direction, okay? Both of these do the same thing, okay? So we basically take all of that entire effect and we put it into this term right here, mu, okay? And so the thing to note is that these cohesive forces, okay, if the temperature goes up, okay, generally speaking, the cohesive forces decrease, okay? I don't know what to call this. Cohesive forces go down, okay? And on the other hand, the molecular exchange, if the temperature goes up, the molecular exchange, okay, greatly increases, okay? So if you increase the heat of your fluid, okay, like the cohesive forces are going to decrease, okay, which is going to make it, less viscous, so it's going to make it runnier or whatever. But the molecular exchange is going to increase, which would make it less runny. So these two effects are opposite of each other if the temperature goes up. So it just depends on which one's more important. So like in honey, when you heat up honey, for example, okay, I think you should be able to tell that the most important one if you heat up honey is that honey is going to get less viscous. Oh man, that color is so honey. That's great. All right, so if you heat up honey, it's going to get less viscous, and that's because the cohesive forces in honey are much more important than the molecular exchange. Okay, and generally speaking, in liquids, okay, the cohesive forces matter. Cohesive forces are the most important. Okay, in gases, it's the opposite. Okay, the exchange is more important. Okay, so that said, when you heat these things up in liquids, okay, so in liquids, if the temperature goes up, the viscosity will tend to go down. Okay, but in gases, if the temperature goes up, the viscosity will increase, and that's because the exchange dominates. Okay, so hopefully that makes some sense. Okay, I think that's pretty cool, and in many ways, not something I ever would have thought of. Okay, so let's go back to kind of engineering-y ways of thinking about this, because normally we don't think about that. Usually, what you do is you just make a point to be aware that mu is a function of temperature. Okay, now how does that affect you? Well, typically what you're going to do is you're going to go to a table in your book if you want a viscosity. And what's going to happen is a problem will say, this particular, stuff has a viscosity of, it'll say this particular, water at a temperature of 100 degrees Celsius, well, that's kind of boiling, 50 degrees Celsius, is doing da-da-da. And you'll say, well, I need the viscosity. Where do I get the viscosity? Well, you just go look it up on a chart, okay? So in our current textbook, looks like it's table 2-3 and figure 2-29. I don't care what textbook you use, though. There's a chart in there somewhere showing you how, showing the viscosity of common fluids at given temperatures. Usually the one for gases is usually like a graph, and the one for liquids is usually you just look it up off a chart. So of course you'd rather work with the liquid because you're going to get an exact number, whereas if you're reading a number off of a graph, it's going to be a little bit more imprecise. Just do the best you can. Okay, so this guy right here, mu. Okay, this is the absolute or dynamic viscosity. And there's another one. Okay, so that's kind of an ugly way to present that, but there's another one which is a mu. Okay, mu is just like a V that's kind of really curvy. Okay, and that's the kinematic viscosity. Okay, now you might be saying to yourself, great, there's two of these, that's really annoying. It is annoying. And the difference between these two is that this one is measured in mass times length per time, and this one is measured in length squared per time squared. Okay, so for example, this one might be kilograms meters per second. Okay, that's pretty standard. And this one might be, let's imagine I'm going to go to the English units. This might be feet squared per second. Okay, there should not be a squared right there, so let's delete that. Okay, so that's just an example, and that's very typical. And really what happens here is that there's a mathematical relation between these two, and it looks like this. Mu equals rho times the viscosity. Okay, you should know this. Okay, that's a lot of Greek symbols. So this is the absolute viscosity, or the dynamic, sometimes called that, kinematic viscosity, and this is the density. Okay, this is really, really annoying. This is also one of the places where it's really, really important. Right here, if you use the English system, like if I were in the English system, you need to make sure you've got slugs here. Okay, slugs, foot, second. Okay, otherwise it's just not going to work out for you. Okay, you're going to have to do that. Okay, and you're going to need slugs here as well. Okay, slugs per cubic foot if you're in the English system. Okay. Anyway, and really what happened here is this. This is the viscosity. But as people were doing all this math and they were like deriving things and blah, 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 they kept coming up with this. They kept having to rewrite this in their derivations. Okay, they had to write that like 10 million times. Like every time they were working through this problem, through these equations, they just kept having to rewrite this. And so finally someone said, you know what? I don't want to deal with this anymore. I just want to call that something. I'm going to call that nu. Okay, and that over time has become the kinematic viscosity. I'm not 100% sure that that's the way it works, but I'm pretty sure. I've run across this problem myself, so. All right, anyway, maybe, just maybe that's not that funny. But, so we want to then go from here, and, oh, look at this. Well, what? Son of a. So we want to come down here, and we want to consider, this case. Okay, and this is the weird case. But it shows up all the time, and it's got a fancy name, and I don't really expect you to know this fancy name. But if you want, this is called Couetflow. Okay, and I'm sure it's named after somebody named Couet. Okay, French person. All right, so anyway, I'm going to just take a second and kind of walk you through what's going on here. There is let's say a table or something. Okay, and this is the table. Okay, and it is in the XY plane. I usually prefer up to be Z, but whatever the case may be, in this case it is the XY plane. Okay, and this table, or whatever it is, has a plate on top of it. Okay, so this is a plate. Okay, just a flat thing sitting on top of it. And rather than having the table sit directly on top of it, we put some fluid in here. Okay, so you can imagine there's some water in there. There's, I don't know. There's some lubricant of some sort. Okay, so and usually you might do this because you want to reduce the friction. So rather than having the plate be pulled along the top of the table, you put some liquid between the two, and now it's easier to pull. Okay, so somebody's pulling this plate along at a velocity v. Okay, which for reasons that make no sense to me, they use a capital V. I highly don't recommend that. And as they're doing that, the fluid is feeling a shear. So at the bottom, okay, there's a friction with this bed, okay, and so the fluid is not moving at the bed, and that's one thing that we're going to talk about in a second, okay, but at the bed, U, that's the velocity, equals 0 when Y equals 0, okay, so there's no movement at the bed, okay, at the top up here, okay, the fluid is moving at a speed capital V at Y equals H, where H is the thickness of the fluid. Okay, so when Y is equal to H, okay, the fluid is moving right along with the table, okay? So both here and here, okay, at these two spots right here, okay, is something called the no-slip condition. Okay, and this is an important thing with fluids. So it says, okay, the no-slip condition, okay, it says a few things. Okay, one, the flow cannot be perpendicular to the boundary. Okay, so basically what that means is if the piece of fluid right here, it cannot, no portion of it can go into or out of the wall. Okay, and that makes, to me, that makes logical sense, because if it could, then fluid could just kind of like spontaneously appear, okay, which is cool, but, or it could just disappear because it's not going to become a part of the wall, right? So that applies at both plates, okay. And then the other thing that happens here is that the velocity of the fluid equals the velocity of the boundary, okay, at the boundary. At the boundary. Okay, so nothing else can happen. Okay, so then the last thing, and this is the kind of, this is the interesting thing, and this is where we're going with all of this, is that the fluid here in between these two, okay, it has a shape here. Okay, in this case, it's linear, and if you've never thought about what it means when people say something linear, it means it's a line. It's a straight line. Okay, it's a straight line. And I'm assuming Newton did these experiments, and what he discovered when he started playing with this is that the shear stress applied to the fluid equals the viscosity divided by, the viscosity divided by the velocity gradient. Okay, so in this case, it's going to be like this. Okay, so this right here, this is Newton's law of viscosity. Okay? And it is really, 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 really important. Okay? Now, to be clear here, okay, this is the shear stress. So remember, the shear stress is a stress. So you can think of it as a force over an area. Okay? And in this case, the stress that is being described here, I'm going to erase some of my scribble scratch here, if this program will allow me. Okay? Is the stress that is being felt between the layers. Okay, so it's being felt between this layer right here and the layer directly underneath it. Okay, if we discretize it, right? Obviously, it's continuous. Okay, so the shear stress right here is being felt between those two layers. Okay, the du dy is also being felt between those two layers. Okay, so basically it's the difference in the velocity of the top layer minus, compared to the bottom layer, and then comparing the distance between those two. Okay, so in this case, the du dy is the same along this entire line because it's a straight line. Okay, the viscosity is the same through the entire fluid because it's the same fluid. Okay, so therefore the shear stress is constant along the whole way. Okay, which means if the shear stress is the same here as it is here, 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 then that means that the shear stress at this surface right here is the same as it is everywhere else. Which means if you know this shear stress, okay, and you want to know the force required to keep this guy moving, you're just going to take that shear stress and you're going to multiply by the area over which it's acting. And the area over which it's acting in this case is this plate right here where it comes into contact with the fluid. Okay, because it's a shear stress. Okay, so that's kind of cool. Okay. All right, so let's consider. Whoa, that is not what I meant to do. That's kind of fun though. Let's consider another case. Okay, so let's go over here. Let's grab this case. Let's bring it down here. We'll make it appear right there. All right. So this is not Couetflow. Maybe it is, actually. I'm not 100% sure. Not really important. I don't care what you call this. Okay, but I want to look at this fluid and I want to think about similar sort of things. So if I stare at this, now this is kind of a similar situation to the last one, but now we've got a fixed plate on the top, so this thing's not moving. This one's not moving. So this could be flow between two plates. If you wanted to think about this other ways, you could think about this as flow through a infinitely deep river, like if we were looking down on the river. That might be a good way to think about this. If you want to think about this as flow through a pipe, you've got a fixed kind of the top of the pipe up here and the bottom of the pipe down there. Now, of course, we're not considering the other, the roundness of the pipe all the way around. So we're just, flow between two pipes, between two plates, excuse me. And what we can see here, if we look at this, is a few things that, are going to remind us of this law of viscosity, Newton's law of viscosity, is first of all, notice, just like on the last one, we have the no slip condition at the walls. The velocity at the walls is the same as it is for those boundaries. So the boundaries aren't moving, so the fluid is not moving at the edges. Which means that, well, why is there fluid moving at all, right? If there's viscosity, so if viscosity exists, if the viscosity exists, then, as I was saying earlier, the effect of the viscosity is to try to make all the fluid flow the same speed. So if there's no fluid flow on the edges, why is there any at all? And I'll tell you that, and this, is for further along, but basically it's because the pressure on this end of the pipe is higher than the pressure on this end. So if you can imagine, like if this were a pipe or something, usually what that means is this end is open to the atmosphere, is open to the atmosphere, and so it's like at atmospheric pressure, and this end is pressurized above that, and so the water flows through the pipe, and that's why when you open your faucet, it comes out, because you have low pressure in the atmosphere where you open it, and you have higher pressure somewhere else, So anyway, so that pressure is what's maintaining this velocity. Is basically because it's higher pressure, upstream than it is downstream, the fluid is trying to move to the right, but it is being impeded by the friction, on these, on the boundaries. So what I want to think about here is, you're hearing my Rocky dog. Rocky, shh. So you're hearing, anyway, so there's, so one thing to note is that we want to think about where the stress is in this fluid, And so the way we look at that, so a lot of times you might a lot of times the question might be, what is the stress on the fluid itself? In which case you could draw the entire block of fluid, okay, just the fluid. And you could say, well, let's think about it in terms of, well, there's a stress being applied to the fluid along the top. Okay, it's pushing back to the right, to the left, and there's one being applied on the bottom. Okay, so that, if you were to add, let's suppose it's 2 plates, then we could say tau at the top plus the tau at the bottom equals the total stress. Okay, now how would we figure out what that stress is? Well, what we would have to do is we would have to look at this equation right here. We would say, okay, well, we need a mu and we need a shear stress. So we're going to want to get the mu of the liquid, so whatever the liquid is, or the fluid is, so we're going to have to look that up in a chart somewhere. Okay? And then we'd have to say, okay, we got that. Now we need to get this, du dy. And we're going to want the du dy applied at the edges. Okay, so I would go down here and I would say, okay, well, what is the du dy right here? Okay, if I can draw a tangential line, and I could do the top or the bottom. By symmetry, they should be the same. Okay, and we would have to just, either do our best, or if we knew the equation of this line, we could figure out du dy. Okay, and that's how you would solve this. So you'd plug in the viscosity here and the strain rate right here. Okay, or the velocity gradient. Okay, so that's how you would solve it. Now, the other thing that I think is really interesting in this case is, what about right here? What's the shear stress there? Okay, what is tau at the middle? Okay, well, the viscosity we would look up in a chart. But what about du dy? Okay, and I want to think about the 2 layers. I want to think about the layer right here. Okay, and the layer infinitely close to it, but right there. How much is the velocity changing with respect to y? Well, they're separated by a distance dy, but the du, well, they have the same velocity, right? Since they have the same velocity, this is 0. Okay, this is, whatever dy is, the smallest, dy it can be, but it doesn't really matter. This whole thing is 0, so it's 0. There's no stress at the middle. Okay, and that should make some sense, because if you think back with what we were just talking about with viscosities, a particle in the top layer, so a particle moving down the middle right here, okay, and the particle in the layer right next to it, well, look at them. They're pulling on each other. Well, great. They're basically holding hands because they're both going the same speed, so there's no stress between them. That's very easy for them. Okay, and if they exchange positions, well, that doesn't have any effect either, because what difference does it make? Okay, so the shear stress in that case is 0. So the shear is highest on this edges where you can see what this what the velocity gradient is, and it is least here where the velocity gradient is 0. Okay, so it's a pretty complicated idea, but really, 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 really important. So so give me 1 second, and let's grab this guy or girl or whatever. It doesn't really seem like it has a gender to me. And let's go over here and let's work an example here. Okay, so glycerin at 20 degrees F is used as a lubricant between a stationary surface and a moving plate. Okay, so we're going to want to draw a diagram, a picture, because that kind of helps us. So this is a stationary surface, and we've got a stationary surface and a moving plate. Oh, well, this kind of looks like my picture from earlier. Here's a moving plate. We've got glycerin in here. Glycerin. Okay, it's just a nice song from my era. Use a lubricant between a stationary surface and a moving plate with an area of 2 square feet. So the moving plate, this little area on the bottom of this sucker, okay, the area is 2 square feet. Okay, let's see what else. The glycerin is a 1/4 inch thick, so that's 1/4 of an inch. Achi-machi. Don't really like inches, so we will end up changing that to feet. We'll go ahead and do that, 1/48 feet. Okay, so this is my given. And the plate is moving at v equals 5 feet per second. Well, I picked a really bad spot to write the area. V equals 5 feet per second. If the shear is constant in the gap, okay, that means that the fluid is going to be moving like this. Okay, so the shear just means that this is constant. So it means it's a straight line. Find the shear stress and the force required to generate the stress. Okay, so required, the shear stress, okay, equals what? And the force equals what? Okay, so now we're going to solve this. Okay, so there's no free body diagram on this because we're not really going to be analyzing a whole bunch of forces and things. But we can say that tau shear, okay, I wish I hadn't written that word shear because now I'm going to have to write it again and again, but it's okay. du, what direction is this? I'm going to make this z because I prefer z and x. Okay, so z and x. Some of you will prefer y's. I don't really care. I just like z's. Okay, so tau shear equals mu. Well, what is mu? Well, we have to figure out what mu is. And so what we do is we go to your textbook, and it's got a mu for us. Or maybe it doesn't. Okay, and well, so I'd have to give this to you in class or something, where we make sure, and the reason is, so your book has this, but it only has it for the SI system. So for the English system, you're gonna have to look this up elsewhere. So we'll establish where you look that up. If basically, if it's not in the FE equation sheet, which is on Moodle, then you're just gonna have to put a letter there and move on, because basically I've cheated you, and I'll give you those points back when I grade. But usually it's going to be provided for you either in a table in your book or on that sheet, or sometimes it'll just be written up here. But here we have to use the English system because we've got Fahrenheit, we've got feet squared, we've got inches. Okay, so we don't really have any choice. All right, so now du dz, and this is kind of the more interesting question here, is how do we get at this? Okay, we don't know the equation of this line. If we did, we could take a derivative. However, we do know that it's constant. So since it's constant, we can estimate it by saying, well, what is the difference in velocity? Well, we're not even going to estimate it. We're going to be exact in this case. What is the change in velocity from here to here? Okay, so we're basically getting the slope of this line. So the change in velocity up here is 5 feet per second. Okay, the velocity down here is 0 feet per second. Okay, now how much did z change? Well, z went from, at the top, it was 1 over 48 feet, and down here it was at 0 feet. Okay, so the change in velocity over the change in height. Okay, so we can plug all that in. We get 708. Okay, now we need to consider our units. Okay, so we've got slugs. Okay, nothing's going to cancel that out, right? Foot seconds, so we've got, so this thing right here has units of feet squared per second, it looks like. Nope, it has units of per seconds. Okay, 1 over seconds. Okay, so this becomes slugs over feet times seconds squared. Okay, and if we use the fact that 1 pound force is now remember F equals ma, so that's slugs times feet per second squared. Okay, then we can kind of take this thing and we can turn it into pounds. Well, let's not forget the number. Why won't you let me erase? So resistant. Okay, 708 pounds per foot squared, or PSF. Okay, as you will often see me write this as 708 PSF. Okay, I like to report 3 significant figures, so we're good here. So normally I would ask if you have questions at this point. This is a little bit confusing, or can be. So stare at it, make sure it makes sense. If you can't figure it out, talk to me. Okay, So that's the first part. The second part is we want the force, okay, required to make that happen. Okay, so the force is being applied on this plate at the top. Okay, so it's going to depend on how big that plate is. Okay, obviously if that plate were, the size of a football field, it's going to be a lot harder to create that sort of shear in the fluid than if the plate is, in this case, 2 square feet. Okay, so basically what we're going to do is we're going to say take the tau shear and multiply times the area. Okay, so it's basically the area over which that shear is happening. Okay, so in this case, this is almost trivial. So we can complete this, we just kind of plug and chug. We get F equals 16 pounds. This is technically pounds force, but I don't, after, the first couple lectures, I never put the F there because I only use pounds force. I don't use pounds mass. And then we want 3 significant figures, so we round it off and we use the pound symbol because that helps us out. Okay, similarly, we can do this again in a similar manner. If I can find, yes, this friend. So let's move him over here. And let's zoom and let's see what we think. Okay, similar problem. So let's kind of look at, this sort of possibility. So if we say, well, all right, so here's a velocity profile. I'm going to use the one that I used from earlier, although, I'm going to have to change a few things maybe. It looks like they're dealing with capital V's. So this is a capital V and this is a capital V. Okay, so when it says if the viscosity is 10 to the minus third newtons times seconds per meter squared, find the maximum and the minimum shear stress. Okay, so this is kind of our given right here, but also we're given this table. Okay, and what that table says is, oh look, at a distance y in millimeters. Okay, so y is being measured from here up. Okay, if we're 1 millimeter above that thing, well, here's the velocity. If we're 2 millimeters above that, well, here's the velocity. If we're 3 millimeters above that, here's the velocity. Now notice that the change in velocity, okay, is decreasing as you get further away. And that we would expect because eventually you're going to get to a point where it's going to start to decrease, right? So, basically it's the velocity is increasing, but the rate at which it's increasing is decreasing. Okay, until it is no longer increasing and now it's decreasing. Okay, so that's kind of what we would expect. Okay, so we want to find the maximum and the minimum shear stress. So we want to remember our law here, tau equals mu du dy. Okay, and we want to identify where the maximum and the minimum shear stress are. Okay, so this thing depends on the viscosity of the fluid, which is defined. It's the same everywhere, so that's not going to have an effect on the maximum and the min. But this is going to change, okay, the du dy. So, for example, the du dy between these 2 points, between, say, this point and this point, well, the change in velocity, well, I guess we could make this a capital V, okay? The change in velocity is 0.98 meters per second. And the distance between those two is 10 to the minus 3 meters. Okay? Now, if we were to go between the next 2 points, it would be going 0.99 meters per second. And over here, it would still be 10 to the minus 3 meters. Okay? So notice if I put this number right here over that number, it's not going to be as large as if I put this number over that number, right? And so the logical place for the biggest shear stress then is where there's no velocity and the y is 0. And we know that it has to be right here because that's the no slip condition. So we know we have no velocity here, and we have, and we're at the wall. So again, this is going to be 10 to the minus 3 meters. And this is going to be 1.00 meters per second, difference between those two. Okay, so that's where we're going to have the maximum shear stress. So tau max equals 10 to the minus 3 newtons times seconds per meter squared. Okay, and then the dV is 1.0 meters per second. over 10 to the minus 3 meters. Okay, and if we work all that out, I have to look at my work here. Tau max, awfully boring when everything's, I don't know why I have to look at my work. Look, boom, boom. And then you just have to do the units. And this comes out to 1 Newton per meter squared, which you should know is 1 Pascal. Okay? Okay, that's the max. Now, some of you might be saying, wait a second, this is totally an approximation. Hopefully some of you said this is an approximation. It is an approximation because we're using a point at, we're using a point at 1 millimeter to estimate what's happening right at the wall. Okay, obviously we'd really want to go between 0 and 0.0000000, like ... 1. Okay, and then over here do, a velocity of 0 and whatever the velocity is right there. Okay, we don't have that measurement, so you just do the best you can. Okay, now what about tau min? Okay, we should already know the answer to this because the minimum, the minimum is right here because there's no change in velocity right there. So it's all positive stress, or there's always stress going on here. The stress is decreasing, decreasing, decreasing. Hits this point, boom, equals 0. Okay, and then we have stress all along here. Okay, so that's it. So this is the minimum. Unless you wanted to count like a negative. I suppose maybe there's a negative stress over here. I don't know that I would ever do that. I think it could almost be an understood absolute value here. Don't write the absolute value here, but if I ever ask you for the minimum is 0 as long as there's an inflection point. Okay, so that would be my recommendation. All right, so the last bit of this, and this is one of my favorite things to talk about, and this is where the oobleck comes in. Let's see, we're going to go over here. We're going to go to one of my favorite things. This is from the old textbook. You can find this in like every textbook, right? Everybody does something like this. Okay, now what we've been talking about this whole time is we've been talking about this. Tau equals mu. I'm going to use the symbols they use in this chart, dv, dy. Okay, but it's not any different than if we use u. U is, so I should have said that earlier. A lot of times we use u instead of v. Well, there's some very good reasons for that, but just understand that, well, just for now, just accept it, okay? We're going to use u for v sometimes. But in any case, and so what I've been showing you is this, okay, this relationship, which is really powerful, okay? And so if I were to plot dv dy against the shear stress, okay, I can get the slope of that line. So like right here, this is a Newtonian fluid. Okay, the slope of that line is the viscosity. Okay, so basically you could think of this as y equals mx. So this would be y equals mx plus b. Okay, now notice in this case the b for that line would be 0. Okay, the slope is the viscosity. Okay, and then the tau is on the y-axis, and the strain rate, or the velocity gradient, is on the x-axis. Okay, so this is this slope right here, that's your viscosity, mu. Okay, now for most fluids, or maybe not most fluids, but the fluids that we work with, we're going to consider them to be kind of ideal. Okay, meaning that they are going to be Newtonian, which means that the slope is constant. Okay, this is not always the case. Okay, and as you can see, because there's some other ones that are written on here. So I'm going to kind of try to give you an example of a few that are different. So for example, okay, this morning you probably woke up and you brushed your teeth. Okay, and there was a tube of toothpaste like this. If you turned that toothpaste upside down and you held your eye under it, okay, I don't know why you would do that, but I have done it in a class demonstration before. Okay, what would happen? Well, obviously, if it were a fluid, okay, or if it were a traditionally defined fluid, it should flow out into your eye, and that would really hurt. Probably. I don't know what you brush your teeth with, but probably not a good idea, not recommended. Okay, but what's going on here? Well, your fluid, but I think most of us would probably consider toothpaste to be a fluid. You wouldn't consider it to be a solid. Okay, so if you squeeze it and it just, and so what happens is basically it's got a certain shear stress that it needs to reach before it starts to behave like a fluid. Okay, so for example, your toothpaste in this case, okay, is what we call a Bingham plastic toothpaste. Okay, so it has like right here, you can see the slope is infinite. Basically, it's got like infinite viscosity. Okay, until you get above a certain shear stress, and then all of a sudden, look, it's going to behave just like the Newtonian fluid. Like maybe it's got a different slope because maybe it's got a different viscosity, but it's a linear relationship between the two. Okay, so toothpaste is a very good example. Another thing that you can think about toothpaste is if you were to put it like if you like had a plate and you just squeeze some out. I mean, you think about always like in the perfect commercial, it's always kind of got that like that little thing like that. They put it on the toothbrush or whatever. Okay, ignore that first line, and it holds its shape just like a solid. Okay, it doesn't need a container. Okay, but once you get it above a certain shear stress, it behaves like a liquid. It flows out onto your toothbrush. Okay, it flows out as soon as the stress is released by exiting the tube. Boom, you got toothpaste. So that's pretty cool. Okay, now there's other examples that are of things that are not Newtonian. Okay, where essentially this relationship changes because of these two things, and this one is called shear thinning. And so in these things, the higher, so you can see that for low values of dV dy, so if it's not flowing very fast, okay, or the shear, the velocity gradients are low, okay, then the viscosity is going to be high. You can see the slopes over here are relatively high compared to over here. Okay, so basically, it is thicker than over here than it is over here. Okay, so it's thinner over here. So that's why they call these shear thinning fluids. So basically, the more you stir these things, okay, the thinner, the easier they are to stir. Okay, and there's two really good examples of this. I don't know if you've, just thinking about that, I think about my summer project where I was dealing with paint. Okay, and when and the faster you spin the paint, and like I've done this many times, you stir the paint, and the faster you stir, the easier it gets to stir, which is pretty nice. Another really good one is blood, and that's like really good for blood because when it starts to slow down. Okay, it will thicken and clot, which is good, although the clotting is really complicated and has a lot of chemistry involved, which I don't know. But when it's moving, when it's going fast, okay, it behaves like a thin liquid, and so it's not stressing your body too much out to move it. So that's like awfully helpful. Okay, so now the last one here, this is the shear thickening. So now this is like really cool and like almost is very difficult to imagine. And what you can imagine, what's going on here is down on this end, it's thicker. It's thinner, and it's thicker over here. Okay, so that means is the faster you spin it, the more it behaves like a solid. The thicker it gets. So it starts to kind of like. You can imagine viscosity getting more and more and more until it's like, behaving like a solid, okay? And the best example of this is something called oobleck, okay? Now, oobleck is very fancy and very cool, and I'm going to refer you to a video. I would show you a video in class, and basically there's a video here, and I highly recommend you watch it. But what's cool about oobleck is a lot of things. First of all, the name comes from Dr. Seuss. Okay, and it's basically a name for some slime. Okay, and so You make oobleck by mixing cornstarch and water. I once made this on a date. It was a very successful date. We had a lot of fun, and we dated for about a year afterwards. And it was like, it was just totally fun. And you will make a mess. And what happens is when you put the cornstarch in the water, now I warn you, the longer you let it sit, the chemical properties of the oobleck kind of changes. So you might have to adjust the ratio, but you're gonna pour the cornstarch and water in here. And as you stir it, if you stir it fast, it behaves like a solid. Or you can like pick it up, and as long as you're punching it and squeezing it and doing things, it'll be like a solid. And as soon as you let it go, it will just turn back into a liquid and slide through your hands. Okay. The other cool thing is one of these videos I'm going to show you. So there's going to be at least 2 on oobleck. But one of the other things that you can do is I found this great video. There's lots of videos of this where these guys fill a swimming pool with it. Okay. And the cool thing about having a swimming pool full of oobleck. Okay. Now we're going to draw it as if it has a free surface, because it does, sort of, as long as it's not being strained. Is that if you jump on it really hard, okay, you can bounce off of it. But if you just stand on it, you will sink into it. Okay, so I think of it kind of as quicksand. Okay, and these guys, they create a pool of it, and you can see waves on it, et cetera, but then they can run back and forth across it. Okay, and it's pretty awesome. So I highly recommend that video. I'll put it in the link or whatever. I'll put it down here. Okay, so the first comment. And if you didn't do it last week, so I highly recommend going to look at those ones of the cavitation and things like that. All right, so we are at 56 minutes, so it's a little bit shorter than last week, thank God, because the Tuesday lecture, because that one was really long. And that's it. So I hope y'all are enjoying this hurricane right now, and nothing's really happening. So again, take care of yourselves, take care of your family, hurricane, take care of your property, and be easy, and that's it. So let's do the zoom out so we can see what mess we made. The nice thing about never having to erase, there it all is. See y'all, have a good one. Bye.